So as you will have noticed, we didn't get as far as I would have wanted, but I have the permission to jeopardize the discussion session and maybe to move some of what I'm going to talk about to the discussion session. So maybe during the discussion session, we'll start by talking about cluster varieties as a generalization of toric varieties. And it is from the point of view of what I will say in the second half of today that will hopefully be a very natural generalization. And also, if you take this point of view that I'm introducing here, then questions like a natural basis for sections on line bundles on the toric varieties, this type of question becomes very natural. And as you will have noticed, I keep emphasizing that we have a lattice of tangent vectors, and that will really be important in order to obtain a basis of sections. And then after that, provided there is time, we can have some more informal discussions. We can talk about some ideas, discuss some examples, and if someone, for example, wants to present an idea of their own, they're welcome to do so. All right. So we'll try. There are many different formats in which this could be turned in an interactive session. I think it'll depend a bit on how many of us there are and how much time there will be left. All right. So we discussed about what a toric variety is yesterday. For today, and in fact for all of today, I will restrict to surfaces because it's easier, though everything does generalize to any dimension. So this is a toric surface. It's always useful to have some images in mind, and that's definitely the case here. Oh, I'm finding some hidden chalk that I can break. Okay. Yeah, you were hiding that chalk from me because you knew I was going to break it, but I will break it now. Anyways, so a toric surface we can think of, as you know, it has a C star inside. So it has D is D1 plus DL. So there's a decomposition into strata.
Those are not good colors.
Those are not good colors. Okay, both of them are not good?
I put some.
I see. Yeah. Okay. I will follow your guidance. So I'm a bit colorblind. So in general, there's some colors I see really well on the blackboard. And then those are colors usually, people who are not colorblind don't see. And vice versa. So I see, so this is a color you don't see. Oh, wow, yeah. So I see this perfectly. But like red, I would have a lot of trouble. So what about, do you see this one?
No, you have right.
Okay, yeah. I will follow. Yeah, all right. I tried to rebel, but I failed. So I give up. Yeah, anyways, there's as a colorblind person, it's always a bit annoying because people tell you, look at this green thing over there, and I'm like, what green thing? But there's one moment where, I can use some colors that only I see. Anyways, all right, so D is D1 plus DL, yeah? And then we can think about the divisor as lying at infinity. So this is the boundary. Yeah, this is boundary at infinity. And then we saw that we have some interior C, well, in this case, C star squared, which is the complement. So this is the interior. And then last time we talked about how following one parameter subgroups, following co-characters, we like, explore what the boundary looks like. Maybe this is D1, D2, and DL. So now the fan, one way of thinking about the fan is, well, I told you it's co-characters, and so one kind of useful way of thinking about this is, well, it's dual to divide. I mean, every ray of the fan corresponds to a divisor, and this kind of this is a useful way of drawing it. I mean, it's also not like incorrect, because I remember I told you we're following some one parameter subgroup, some map from C star to C star n, and then we end up at the generic point of the divisor if we're on this ray, and then the other cones do correspond to these toric points, yeah, codimension 2 strata. Okay, so we have cones, etc. All right. And maybe we call this row 1. I mean, actually, we did call it the D1 dual, D2 dual, DL dual. Okay, any questions for this? Then we saw that we can look at some curves inside our toric surface, and we can take their tropicalization. The way I introduced it to you yesterday, the curve was basically inside C star squared, and it had some asymptotic behavior. And then if you tropicalize it using what I described to you yesterday, you get a so-called tropical curve, which sits inside the fan. So N was the lattice of co-characters, and then we define the fan of S in the tensor product of the lattice with the reals, vector space. So R2, this is isomorphic to R2. Right, and then these, right, always these kind of integers that I keep, these are these integer points that I keep talking about. So this is a tropical curve, I don't know, maybe T inside NR. And then if the curve has, if C has tangency profile, I mean, it has some tangency profile with D, and then the tropical curve will have the same kind of tropical tangency profile, so with corresponding tangency profile. Corresponding tropical. So what is this tangency profile? This is, meet. This is meet di. So we can say maybe so. What the tangency profile is a collection of pi on C, and then the requirement that Pi should meet Di in tangency Aij. So, and then C meets D at Pi, meets Dj at Pi in tangency Aij. Yeah? And then this corresponding tropical tangency profile becomes so rays asymptotic rays. I mean, rays are asymptotic. Rays maybe rho I in so rays in direct. Okay, maybe. So the rays go into the direction of dj dual sum over the Aij with correct weights. So yeah, maybe I don't want to like I don't want to like get lost in details about this, so I'll just show you some examples. So if it's so maybe for example, it could be Pi meets well D I don't know, SI. I'll just do an example. Sorry, I didn't want to like go into details about this because we're going to lose another 20 minutes, but let's just do an example. Let's just do an example. I think this is maybe more instructive. So we have in this example, for example, we could have something like this. So this was, let's say this was DL. This is maybe D2, this is D1, and this is D2, 3, 4, 5. And then we could require the tangency here to be maybe 2. Oops, maybe the tangency should be 3 here. The tangency here should be maybe, let's just say 5 and then 1 here. Yeah? So what would this look like? So the rays would be, so the DL gives us this direction here. And then we have 2 points. So that means that we have 2 rays in the direction, this is the direction of DL star, DL dual. And then they have weights, they carry, so this is the direction. If I take the first integer point, the primitive point on this ray, I have the direction DL dual, and then it carries a weight, which is 2 here and 3 here. Okay? Then it also has a direction D2 with weight 5. So this is, I mean, D2 is this direction. I should put it over here. Has weight 5, and then it does have 1. Okay, so the things don't really match up, so I'll just put, maybe I'll put 5 here. You'll see why. And then there's 1 in the direction D5, which is of weight 5. So this is the asymptotic bit So this is the asymptotic rays, if you want. And then there's a like area. There's a kind of there's a bounded area, and in the bounded area we have a graph with so it's a metric graph where the edges are directed by primitive elements in N. In our lattice, they carry some weights, and at each vertex, the balancing condition is satisfied. Which is that if you have a vertex V and you have a bunch of primitive generators, UIs, which carry a weight WI, then the sum of the WI UI should be equal to 0. Okay? Balancing needs to be satisfied. So what does such a thing look like? Well, in this example, it could be, I mean, the easiest thing that could happen, for example, is something like this, where, okay, this is maybe not, maybe we want something, so we have a 5, and then yeah, okay. I'm realizing this is, I need at least another one here. So let's say we have another one, 3. Sorry. Then we'll have maybe something like this, and then we could have something like this. This is an example. And at each vertex, at each of them, we have that the sum, this balancing condition is satisfied, meaning the sum of these weighted by the weights should be equal to 0. And maybe this works. Let's do another example, which is the one we're going to use in a second, which is applied to let's say, maybe we take this one, D1. So here's where I go a little bit more general than yesterday, because yesterday I always assumed our curves to generically be inside C star squared and only meet the boundary in a bunch of points. But here I really take a curve in the boundary, and it's important to do that. But the whole story also works. So if you apply this to D1, what we get is, well, D1, as you can see, meets DL in one point of tangent C1. It meets D2 in one point of tangent C1. So meet D2 in one point, tangent C1, meet DL in one point of tangent C1. But it also meets itself, right? It intersects itself, so meets itself in tangent C D1 squared. Well, what is D1 squared? D1 squared is the degree of C1 of the normal bundle of n1 in S, which is an integer in Z. How should you think about this? Well, I mean, this is D1. We take the normal bundle over it. Now, if there was a generic section, then so if this was a generic section, so then the self-intersection will be, well, you take a generic section, so you move away from the normal bundle, and then you intersect the like deformation of D with itself. That gives you a number. And what I just described to you is, C1. And so we take the degree of C1. Now, if you don't have a generic section, then, you have to think a bit harder what that means. But in any case, D1 is isomorphic to P1. So that means that the normal bundle, of D1 in S is going to be isomorphic to some O of D. And then this degree is just this D here, D in Z. Yeah. Yeah, so applied, so here I described to you a process that I didn't give in full details to save time, which is that if I have a curve inside S, I can tropicalize it. And now the process of tropicalization I introduced yesterday as, you take log of, you intersect it with the complement, with the C star to the C star squared, and then you take this log map with log T map, and then you take T going to infinity. But there's a more general definition that you can use, and then in any case, the outcome is a tropical curve. So right now, I'm applying that process to the curve D1, which you can see here. Yeah? So D1 has, so in this tropicalization process, we get a tropical curve, and then the tropical curve has some asymptotic part, which is about the tangency profile with the divisor, and it has some interior part, which is about this balancing condition. And now I just want to see, in the case of D1, what is the outcome, and then I'm going to use this later. And the outcome given what I told you, the only thing we can say is the following. Yes? Well, so it could, but it doesn't have to, right? It need not, yeah. It may or it may not. So in general, that's why, in this example, so basically, so if you have a curve, then it meets the divisor in some way, and then the tropical curve will meet the divisor in some way, and then, sorry, one more time. If you have a curve, then it meets the divisor in some way, yeah? Then the tropical curve will have these asymptotic, like rays, weight with direction and weights, and it will have this kind of interior part. The interior part needs to satisfy this balancing condition, and now if you figure out that this is not possible, then that means your curve couldn't exist. No, it will meet the divisor in general. Okay, so in the case where in the toy case, the interior is C star squared, and then whatever like map you have from P1 into S, it will, the only way you can map P1 into this is the trivial map. Yeah? So what I'm trying to say is that if S is toric, then the image of F, so F of P1 will intersect D. This is never going to be empty. I mean, if D is non-trivial. I mean, there's a result that tells you this. But it doesn't have to intersect every divisor, yeah? For example, if I take P1 times P1, which looks like this. Well, I mean, this curve here intersects, you know, I mean, this is, you know, so we have one P1 here, we have one P1 here, right? P1, P1. And then there's a map from P1 inside here that, you know, maps to a copy of P1 over maybe the point, I don't know, 1, 1, yeah, for example. And then that thing will not meet the divisor, yeah. So it really doesn't have to, yeah. And now if I apply this in this situation, which is if I take a toric divisor in a toric surface, you can see that, I mean, from the way I drew it, but you know, it's also, I mean, if you think the boundary is the closure of the one-dimensional torus orbit, and then you know, you can figure out that, well, each boundary component will meet two other boundary components, but it won't meet the others, yeah. And then you can figure out that you, this D1 meets DL in one point, D2 in one point, and it has it meets itself in like its self-intersection. And this means that the tropical curve, I mean, so this one exists, right? And so this means that the tropical curve of D1 satisfies the following. So it has a ray D2, maybe. So it has a ray which is D2 star. It has a ray which is DL star. And now to make this balanced, I can tell you right away what, I mean, you can see from the picture that it has to go in that direction, right? You can see that, I mean, balanced means, you know, if this was, I don't know, 2 minus 1, and this was minus 1, 2, I mean, those are random numbers. Then this one has to be, you know, minus 1, yeah? Or maybe we'll take, I don't know, we'll take maybe 3, minus 1, and minus 1, 3. Then this one has to be this one with weight 3. Yes, so this, that's right. So I'm saying that, so D1 star is actually this one, right? But in this picture, you can see that, well, in here you can, if this was the case, you could conclude that, I mean, so the curve, so the balancing here tells you that, well, DL star plus D2 star plus A times something, maybe I want to put the D1 star in the middle. So let me say that. So we have D2 star plus A times D1 star plus D2 star is equal to 0. That's the balancing. I mean, I could put some weights in front of them, but I know what the weights are because they're the tangency, right? So this is weight 1. And because of tangency. Yeah? I mean, same here. Exactly, that's exactly the point. That's exactly the point, yeah. A is D1 star, so D1 squared, exactly. That's exactly my point, yeah. And it could be negative, yeah? So you can see that in this case, for example, it would be negative, yeah? Okay? So the curve gives you some relationship in the fan, and in this particular case, you can read off the self-intersection. And yeah, that's where I'm getting at, and we will be using this shortly, actually. So summary. And this is important, you know, this is very important in order to, I mean, I'll tell you why it's important afterwards. So we've just proven, you know, proposition, you know, so if we've proven that if you take di minus 1 plus di plus di plus 1, where we we take I mod L, right? So if we take the indices mod L, then it's equal to 0 if we provided we put here di squared. And we'll be using that. So yeah, we just proven this fact. Right? More questions?
So given any curve in S, you kind of trying to include some fundamental information by how it meets the boundary divisor. In this example, you're viewing V1 as a curve.
Correct. Absolutely. So I'm trying to, I'm really advocating this philosophy. I mean, maybe not philosophy, but so we have curves inside our surface, and they interact with the boundary, and then their interaction tells us something about our fan. And this is something that will be very important also for the cluster varieties. Yeah, we have the divisors are, yeah. Well, let me apply this right now. Let me apply this right now. So we really have the curves are probing our variety, and then we're going to be using this. We're going to be using this. Let me give you an example. Let me tell you right now how we're going to use it. So application. So D, you can think the Prakhar dual of D gives you an element of H2. So this is, we had a discussion about this yesterday. So here, and in fact, by construction, this divisor is C1 of S, which I mean C1 of T of S. That's this is the Calabi-Yau condition. This is, so because SD is log Calabi-Yau, or because D is, I don't know if these things mean something to you, but because D is anti-canonical, I briefly said yesterday that being log Calabi-Yau means you have a holomorphic volume form that with like a simple poles along D. So one way to phrase this is by stating it this way. So C1 of the tangent bundle. Then we have a curve. A curve gives us a curve C, gives us an element C in H lower 2, S to Z. And of course, you can pair elements of H upper 2 and H lower 2, which gives you an integer. So we have dPd times C gives us an integer. So this is similar to what we've done, except that what we done was more refined. Yeah. When we did these intersections, we were looking at intersections with each of the divisor. This is just a kind of global homological intersection. And so then definition, so, D is ample if and only if, this thing here is positive for every curve. Now, this is not the way usually ampleness is defined, but it is an equivalent way to define ampleness. So it means that the divisor meets any curve positively. And it could really happen that it meets it negatively. For example, you could see in this example, if we had just, so here d1 squared, in this example, d1 squared is minus 3. Yeah. So I mean, what does it mean? Intersection minus 3 means, the way I defined it over there. It means that the normal, particularly, it implies that the normal bundle has no sections, so you cannot move the curve away. And now, using what we have discussed, we can see that we can characterize what it means for surfaces to be ample. So, so surface, I mean, a surface, a definition. Now, S is Fano if D is ample. I mean, the more general, if outside of the toric situation, the definition, yes? So I couldn't hear it. Oh, I haven't applied it yet. Sorry. Now comes the application. So this is just. I mean, this we could always, I mean, until here, that's not the application comes now. Yeah, sorry. So now application. Okay, so now, sorry, I need to formulate this well. So let me just tell you the proof, and then we write down the result. So if I take so this is a surface, this is a toric surface with its fan. Now we have this condition, yeah. So D times any curve, but in particular I could look at D times DI. Yeah. So I think this is a DI dual, and then I can compute the intersection of this, yeah. And then we know, I mean, so D is well, D1 plus DL. So from the computation we did before, so this is DI, this is DI minus 1, this is DI plus 1 dual, where again we take the indices mod L, and then if I compute this, we get, I mean, DI won't meet the other ones, it'll just meet this and this, and it'll meet each of them in 1 point. Yeah? Bless you. So this is going to be 1, which is, this is an intersection with DI star. And then there'll be another one here. So this is with, so this one here is, DI plus 1 star times, well, times DI. This one is DI minus 1 times DI. And then there'll be DI squared. And now you can see that, well, for this to be greater or equal to 1, I mean, this implies that di square has to be greater than -1, right? And so now what we've just proven is that we have, if it's Fano, then it has, at worst, so di squared is greater or equal to -1. But now you also have to prove that this is actually an equivalence. And now if we wanted to start drawing Fano surfaces, so, maybe, so. So this one here, where this is 1, 0, 0, 1, 1, 1, this is okay, because, if this is di star, this is okay, di star is greater than -1. And you could always, up to an element of GL to Z, you could, up to an element of GL n, your first three ways are going to be of this shape, or, or this one, or of this shape. So here we have di star is equal to 0. Right, so here di star is -1, here di star is 0, or this one, where here di squared is 1. You can have more than 1 because, so you can have more than 1, but then it won't be smooth. Yes?
Are you saying that the result is a new application?
No, it's not. It's definitely not new. No. I'm still introducing you. No. It's just basically, if I wanted to show you this, so it is definitely not a new result. It's just, I don't know. It's like one way you could prove this. I'm trying to introduce. Yeah. What's that? Because so 1, 0 plus something times 1, 1 plus 0, 1. For this to be 0, you need a -1 here. Yeah.
So the other two arrows are di -1 star, di +1 star.
That's correct. Yeah. So this is di. This is di -1 star. This is di star. Yeah.
Di squared is the number that's the linear combination with the balancing condition.
Correct. That's correct. Absolutely. And we know that this must hold because there is a curve. Yeah. And maybe, yeah. Okay. More questions? So there's also an immediate application, which is that if we have the other application is, if we go back to, if we had any kind of surface, if we had, a surface. So I should say, here I assumed smooth, which is, I've always been assuming implicitly. If you have a surface, if we have a log Calabi-Yau surface, SD, and we consider its tropicalization, the way we did before. Yeah. Then we can glue adjacent cones we can glue the, we can transport the integral structure from one cone to the other using this relation that I introduced. So if we have, let's say sigma 1, sigma 2 are elements in here, they're dimension 2 cones. If we have so they're maximal cones with intersection codimension 1. So maximal in dimension 2 means this is dimension 2 cones and they are dimension 1 cones. Let's say, let's call them, it is the same situation we had, except that now we're no longer in the toric case, di plus 1. Now I can tell you, I have a lattice of tangent vectors here. So these are, maybe tangent vectors. It's the basis of the tangent space. And now I can tell you how to move this on the other side. And I have a natural basis here. Right? So my natural basis here is given by so di star is this one, is a primitive one. So here I have a basis, in this cone, I have a basis given by di star, di plus 1 star. In this cone, I have a basis given by di minus 1 star and di star. But maybe I shouldn't have drawn, I should have put a little separation because for reasons that will be obvious in a second. In fact, maybe I should have done it this way. So let me redo it just to make things as clear as possible. So what if this is di minus 1 star, di star, and then this one is di star, and this one is di plus 1 star. I have everywhere here I have this basis of tangent vectors, and then as well here. Now I can tell you, so we can move di star, to di star, that's fine. Di star as an element of sigma 1 to di star as an element of sigma 2, that's, we can just move it over, that's fine. But we don't know where to, but where should di minus 1 go? Yeah, so as an element of sigma 1, this is sigma 1, this is sigma 2, where should it go? As an element of sigma 2. And a priori we have no answer to that. But now we have, we can just use this up there. We can use this relationship. Well, actually we're going to move it to. So we're going to move di minus 1 to minus di plus 1 star minus. So we're going to move it to minus di plus 1 star minus di squared di star. Yeah, because these are elements, these are well-defined elements here. And so we can move this one here to whatever that expression is. I don't know, maybe it's here. Yeah. So this is a parallel transport. And then what happens if you're toric? So toric case. If you have, so if you parallel transport around, so you get back to the same. The reason for this is because we have, the reason is, all the sigma i's are contained in NR, yeah. And the way we, we have, you're not, here parallel transport is always, I'm just saying that this vector goes to this vector, 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 and comes back. And yes, so it works because we computed this relationship up there, and then you just, yeah, it just holds. Yes, so you take a parallel transport, so you take a, you take a V inside the tangent. This is a tangent space at the little x. So x is in some sigma I, and then you take some vectors. This is a tangent or tangent lattice. I'm killing the chalk. And then you move it to the next cone, etc., using the definition I just gave you. And then as you come back to, so V goes through all the cones and it comes back to V, if you move around the origin. But this is not going to be the case in general. Sigma x is an element in the cone. So I'm just saying that, yeah, good question. So it's in R2. So I choose a little x anywhere, and at any point I have this, I have a lattice of tangent vectors. So here and then, so x is sigma I is inside R2, is a cone in R2. So x is just an element any point. I have this lattice anyway. And now, for the, basically in general, so in general, so this, in general, any dimension, so in higher dimension, this relationship that I draw up there is generalized to higher dimensions. I won't write it down. But so, as an, so this, so you can apply identification to maximal cones. Maximal cones meeting in codimension 1 cones. And then what you get is you get a integral affine manifold with singularities in codimension 2. Yeah? So in fact, what we're doing is we say that all in codimension 2 cones are singular. or rather, we define how to go from a maximal cone to a maximal cone along a codimension 1 cone, but we don't say anything about codimension 2 cones. And whenever you go around a codimension 2 cone, you get so what I mean by this is, get monodromy. Get monodromy around codimension 2 cones. And then somehow the cluster case can push the singularities to infinity using toric models. And maybe I'll just give you an example of this phenomenon. I'll use a couple extra minutes to give you an example. So if you took, maybe you take P2, well, this is maybe the first example. So we take D1 is, the divisors of this are generated by, H1 is P1 times the point, and H2 is point times P1. So yeah, the different components. So you take D1 to be, linearly equivalent to H1, whatever it means. So 0. H2. And then D3 is the diagonal. So this is the set of, the set of XX inside P1 times P1. X comma X, set the set of X comma X inside P1 times P1. Yeah. So it looks like this. This is the, it looks the same as before, but there's an extra point. This is, I don't know. This is inside P1 times P1. And so if you can apply, apply the process, construct sigma of SD, and you'll see the singularity, monodromy around origin. So we are the only codimension 2 strata is the origin, and if you try to parallel transport around the origin, you get these. You get monodromy, and maybe I'll say one more example, which is if we take P2 and line plus conic, the same thing will be true, but there is one caveat. Same, there will be singularities. You'll have monodromy going around 0. Well, but there's one caveat, which is So this is, we have a line and a conic. This is the line, this is the conic. And so the caveat is, there's the line intersect conic is 2 points. And I didn't say this when I defined the tropicalization, so this is not connected. But we want actually, so to define sigma of x, we want the xi to be always connected. But there's an easy solution, which is a solution we blow up. What does this mean? It means we replace some of the divisor strata by blow-ups. And in fact, the solution is a so-called log blow-up. So the outcome of a log blow-up is so we introduce, so log blow-up a new curve, introduces extra boundary component, and now which is this one. If you know how blow-ups works, it will be clear. And now we can apply the construction. Apply construction now. And then you will see that you get the same situation. You get some monodromy around 0. So you build the cones. Each of the cones has a lattice structure. You say how to move the lattice from one cone to the other using the relation that I explained, and then you'll find you have monodromy around 0. And so this is maybe I'll end by saying this. So tool 1, so log blow up, and this doesn't change the log space. Doesn't change xd as a log space. I didn't tell you what the log space is, but it doesn't change it. So this is one of the first tools we're going to use for cluster varieties. Is we are always allowed to perform a log blow-up. It changes the boundary. It doesn't change the complement. It doesn't change complement. One more time? Yes? So this one is not toric. This is not toric. This is not toric because it's not the toric boundary. The complement is not a torus. So the complement, P2 minus line union conic, this is not C star squared. But it does, so it contains a C star squared, but it's not equal to. Correct. This is also not toric. Yeah, maybe I should have emphasized this. This is not toric. It is clustered, correct. That's right, because that's correct, yeah. So the way I want to define cluster is I want to say that it's a local RBR compactification of whatever you think of as cluster variety. Yeah. Now, with that definition, you're always allowed to change the boundary when it remains cluster. Because, imagine you have a cluster variety, and then you take a log Calabian compactification, which always exists, and then if you change the boundary, it doesn't change the complement, and therefore, it still is cluster. It's the same kind of cluster variety. And so this is the first type of blow-up, which is called the log blow-up, which doesn't change the cluster variety, the log space. And then in order to get cluster varieties, we need to allow more general blow-ups, where you're blowing up some smooth locus of the divisor. In this case, you would be blowing up a smooth point of the divisor, not a strata. And then this will really change the spaces. And then the first step is to say that a cluster variety is something that is log birational to a non-toric blow-up of a toric variety. And if we so for every cluster variety, there is a toric variety such that by performing this type of blow-up and blow-down, as well as some non-toric blow-ups and blow-down, where you blow up some smooth points of the divisor, you get something which is a log Calabian compactification of your cluster variety. And then then using that fact, you'll be able to write down a tropicalization of your cluster variety where the singularities are pushed to infinity. Because we're changing infinity, we're not changing the interior. And so this is, this was going to be my lecture 2 or maybe 2.5, and then the one result that I said I was going to talk about relates to Fano search, and I haven't even gotten to it, so maybe, but yeah, time is too short. Yeah. Anyways, yeah, sorry, thank you.